so here we've got another moments problem. This time it's a child's toy. It's one of those mobile things where you've got some interesting objects and they're suspended from strings. Okay, so all these vertical things here are strings, and then you've got these rods. These are rigid rods that support the whole thing. Okay, now we're assuming that the rods, these three rods here, are weightless, the strings the same, so the only objects that have weight are the objects hanging from the mobile. Okay, and you can see the whole thing suspended from the ceiling or whatever. So the first thing we're asked to do is work out the weight of B and C. Now we're told that the weight of A is 0.4. Now for this thing to balance here, we know that the clockwise moment and the anti-clockwise moment must be equal. Since both of these objects are equidistant from the pivot point, so T, where the string joins the support here, we're taking that as our pivot point. And if this one was heavier than this one, it will pivot to the right. If this one was heavier than this one, it would pivot to the left, or it would pivot anti-clockwise or clockwise respectively. But seeing as it's nice and straight and it's not pivoting, we know that the moments must be equal. This must be 0.4 newtons, okay? Now here, it's a little bit different because we've got, these two are not equidistant from the pivot point. So the pivot point on this one is there, okay? So we've got a slightly different situation. We don't know what this distance D is here, but what we do know is this. We know that this whole object here, so the whole of this object here taken together, so if you take all of that together, that gives you the force acting here essentially is 0.80 newtons, because it's that plus that is essentially acting here. So you've got a force of 0.8 newtons acting downwards from this point here essentially. And then you must have the same force acting downwards here. How do I know that? Well, because the anti-clockwise moment here is 0.8 times 0.1. Okay, because that force is acting at 0.1 meters from the pivot, because we're taking this as our pivot point now. On this side, we've got a force here acting. So the force essentially is acting here. It doesn't matter where these two are situated. The force is acting down through this string here. So we've got a force acting downwards here at 0.1 meters from the pivot. So because they're equidistant from the pivot, they must be the same force. So this force acting down here must be 0.8 newtons, which means the sum of these two objects must be 0.8 newtons. So basically the weight of C plus D equals 0.8 newtons. Now if that's 0.1 newtons, that makes C 0.70 newtons. All right. Okay, so we've worked out all the weights of these different objects. The next thing we're going to do is to work out this distance D. Now, we're assuming this thing's not pivoting at all. It's not, when I say that, I mean, it's nice and straight here. What that means is that the anti-clockwise moment and the clockwise moment must be equal. And we're now taking this as our pivot point, okay? So the clockwise moment must be equal to the anti-clockwise moment. Sorry about that terrible M there. I don't know, I seem to have a problem drawing M's. But what we know here then is that the clockwise moment here is 0.1 newtons acting that way, multiplied by the distance. Okay, force times distance is moment. And the anti-clockwise moment is 0.70 newtons multiplied by D. Okay, now 0.1 times 0.08, we're going to divide both sides by 0.7, and then they cancel out, and that's going to give us D. So D will equal 0.08 times 0.1, which obviously equals 0.008 divided by 0.7. That's going to give you 0.11. So 0.11 meters is your distance. Sorry, that's completely wrong. 0.011 meters is your distance. Okay. So that's that. Now the next bit then, is we want to work out now the tension in these strings. So the tension T, well, we've got 0.7 plus 0.1 acting downwards here, okay? So we've got 0.8 newtons acting downwards. That means that because the whole thing's in equilibrium, the resultant force at this point must be 0. So if 0.8 newtons is acting downwards, there must be a 0.8 newton tension acting upwards. So T is 0.80 newtons. Or another way of thinking of that is the total force acting downwards here is 1.6, because it's those two added up. That must equal that force and that force. Okay, and therefore T is equal to 1.6 divided by 2, which is 0.8. All right, and we know that because the total downward force must equal the total upward force, because there is no net resultant force on any object which is in equilibrium, and we know this thing is in equilibrium. Okay, there we go.